Welcome back. Let's learn how to solve inequalities using properties of addition. Alright, so last time you were introduced to inequality expressions, including how to plot them or graph them on a number line, and how to check if a number is a solution. But now, just like we learned how to solve basic equations, what we want to do is learn how to solve basic inequalities. And the good news is that a lot of the skills that we developed for solving equations translate over to solving inequalities. The processes will look very similar, although the solutions are very different in their meaning. Right, the equations that we solved in the past, their solutions just involved one value for the variable that would make the equation true. But inequalities, on the other hand, have solution sets, which feature a lot of different values for the variable that will make this statement true. And the solution sets can come in one of these four different forms. In each case, we're always comparing a variable to a constant. You could have a variable greater than a constant, such as with x greater than 3, or you could have a variable less than a constant, such as with x less than 2, or you could have a variable greater than or equal to a constant, such as with x greater than or equal to 8, or you could have a variable less than or equal to a constant, such as with x less than or equal to -1. Okay, these are all examples of solution sets that are in the different possible forms that you could have for the solution to an inequality. And so these inequalities here, we would say are already solved, right? They're already in the form of a solution set. And so there's really nothing for us to do in terms of solving for inequalities in this form. But there are going to be inequalities that are not this simple, where the solution set or the values for the variable that make the inequality true are not as obvious. For example, here are some different inequalities that are not already in the form of a solution set. So it's not entirely clear upon first glance what values of x would make these different inequalities true. Okay, we don't know what their solution sets are, but we can solve for it, which is what we're going to begin learning today. Specifically in this video, we are going to focus on solving inequalities like these that can be solved with the help of something known as the addition property of inequalities. And if that sounds familiar, it's because we looked at something very similar when learning how to solve equations. Remember with equations that we learned that you could add or subtract the same value from both sides of an equation, and the solution to that equation would not be changed, right? If we have the equation x equals 4, we could add 2 to both sides and have x plus 2 equals 6, right? 4 plus 2 is 6. And the solution to this equation would still be 4. X equals 4 would still be the correct solution. The solution is not changed by adding or even subtracting a term from both sides. Okay, if you plug 4 in for x here, the equation is still true. 4 plus 2 equals 6 is a true statement because 4 plus 2 is 6. So we have 6 equals 6, which is true. Okay, that was the addition property of equations, but now we're going to look at the addition property for inequalities. And to demonstrate this, I want to start by looking at a very basic inequality, one that doesn't involve a variable. So something like 5 is greater than 2. Watch what happens if we add a value to both sides of that inequality. Let's say that we add 3 to both sides. 5 plus 3 is 8, so we have 8 greater than 2 plus 3, which is 5. And after we do that, notice that the inequality is still true. Right before, we had a true statement of 5 greater than 2. 5 is a bigger number than 2, so that is true. And then when we add 3 to both sides of the inequality, we still have a true statement. 8 is greater than 5. That is true because 8 is a bigger number than 5. And so keeping that in mind, let's now consider an inequality with a variable such as x greater than 2. That right there is a solution set for an inequality, but watch what happens if we do the same thing here. Let's add 3 to both sides of the inequality. If we add 3 to both sides, we'll have x plus 3 is greater than 2 plus 3, which is 5. Okay, so now we have an inequality that looks different than what we had before, but it actually still has the same solution set. And here's how I'll check that. Remember that originally, the values of x that make this statement true are values of x greater than 2, right? If you put 2 in for x here, you'll have 2 greater than 2. That's not true, but the moment you use a number bigger than 2 and plug that in for x, then you have a true statement. If this inequality down here has that same solution set of x greater than 2, the same thing should happen. So to check this, what I'm going to do here is start by plugging in 2 for x, right? If we let x equal 2, then we'll have 2 plus 3 greater than 5, and 2 plus 3 is 5, so we get 5 greater than 5, which is not true, which is good, because 2 did not make the original inequality true either. But now watch what happens if we use a number bigger than 2. For example, what if we let x equal 3? Then plugging 3 in for x here, we'll have 3 plus 3 is greater than 5, and 3 plus 3 is 6, so we have 6 is greater than 5, which is a true statement. 6 is a bigger number than 5. Alright, so when x equals 3, this inequality is true, just like it would have been originally in this form of x greater than 2. If x is 3, then 3 is greater than 2. Okay, so what I'm showing you here is that even after adding 3 to both sides of this inequality, the solution set remains the same. This inequality is true for the same values of x as this inequality right here. If you plug in any number for x here that is bigger than 2, this inequality will be true. And if you plug in 2 or a number smaller than 2 in for x in this inequality, it will be a false statement, just like it would up here. Okay, so what we find here is that adding a value to both sides of an inequality does not change its solution set, just like adding values to both sides of an equation did not change the solution to the equation. Okay, and the same thing would be true for subtraction. You could subtract two values from both sides of an inequality, and the solution set would not change, because you can just view subtraction in terms of addition. You could think of subtracting a number as just adding a negative number. And that would also still be true if we had a different inequality sign here. Okay, it doesn't have to be a greater than symbol. It can be a less than symbol, a greater than or equal to symbol, or a less than or equal to symbol. It doesn't matter. Adding or subtracting a value from both sides of that inequality will not change its solution set. Okay, so altogether, what we have looked at here is the addition property of inequalities, which says that the same number, or even a variable term, can be added or subtracted to each side of an inequality without changing the solution set of the inequality. And the reason why this is important is because we can use it to our advantage to solve inequalities that are not already in the form of a solution set. And so let me show you what I mean with our first example problem. Okay, so here's our example. We are given the inequality x plus 4 is less than 7. All right, and so currently, it's not entirely clear what the solution set is to this inequality, right? We don't know what values of x would make this a true statement, right? This is not currently in the form of a solution set, but we can get it there because just like when we're solving equations, our goal when solving inequalities is to get it in a form such that the variable is by itself. Or the way that I like to say it is that we want to isolate the variable. Okay, and currently that's not the case here, right? We have x plus 4 less than 7. X is not by itself on one side of that inequality sign. It is accompanied by this plus 4. And so in order to solve this inequality, we have to get rid of that constant term, which is pretty straightforward to do. It's just like solving an equation. What we can do is use the addition property of inequalities that I just demonstrated to you and add the opposite of this constant term to both sides of the inequality. So in this case, we would want to add -4 to both sides of the inequality. Or really, you could view it as subtracting 4 from both sides. All right, so if we do that here, if we subtract 4 from both sides, 4 minus 4 is 0. So those two terms cancel each other out, and you'll just be left with x on this side, and x will be less than 7 minus 4, which is 3. So we get x less than 3, and that would be the solution set to this inequality. What this tells us is that for this original inequality, for any value of x that you plug into it that is less than 3, this statement will be true. And so you could check that out if you wanted to. You could pick a number less than 3, such as 2, and plug that in for x. 2 plus 4 would be 6, and 6 is less than 7, so that would be a true statement. And then if you went the other way, if you picked a number bigger than 3, let's say 4, then the statement should be false, because the solution set does not include 4. It only includes values of x less than 3. Or really, you could use 3 itself, since 3 is not included. But either way, if you put 4 in for x, you'd have 4 plus 4, which is 8. 8 is not less than 7, so that's not true. Or if you used 3, 3 plus 4 is 7, and 7 is not less than 7, it's equal to 7. So clearly, this is the right solution set for this inequality. Okay, and then we do like to finish off these examples by plotting or graphing the solution set, just like we did in the previous lesson when we introduced solution sets of inequalities. What I'll do here is draw a number line that we'll use to represent the values of x that are part of the solution set. In the middle, we'll have 0, and then 1, 2, 3. I'll label that with 3. And then you could label other numbers if you wanted to, but the main takeaway here is that the solution set includes values of x less than 3, so you want to draw an open circle at 3, which means we're not including it. If we wanted to include 3, we would fill that circle in, but that's not what we want to do here. So you draw an open circle, and then values of x less than 3 would be numbers to the left of 3 on the number line. Okay, numbers to the right are numbers bigger than 3, so we want to draw our arrow in the other direction to indicate numbers less than 3. And that would be the plot or the graph of the solution set on a number line. Okay, if you haven't seen this before, I would recommend going back to my previous lesson in algebra, but assuming that you've seen this before, then that is it for our first example, and so let's move on to another one. Let's practice solving another inequality with the help of the addition property. Hey, real quick, before we get to the next part of this lesson, if you find my videos here at JK Math to be helpful, then I'd like to invite you to join my membership site JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out, as it's a great way to support me in the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. Next up, we once again want to solve the inequality and graph the solution set on a number line, and this time we're given 5 plus x is greater than or equal to -3. Okay, so clearly this inequality is not in the form of a solution set, so what we want to do is get it in that form. We need to isolate or get that variable of x by itself, and so we can do that here by getting rid of this constant term of 5. And to get rid of it, we need to add the opposite of that value to both sides of the inequality. So that means here we would want to add -5. Or really, you could think of it as subtracting 5. Okay, so if we subtract 5 from both sides of the inequality, 5 minus 5 is 0, so those two numbers cancel out, just leaving you with x greater than or equal to -3 minus 5, which would be -8. So we have x greater than or equal to -8. And that would be the solution to this inequality. That is this inequality's solution set. What this tells us is that any value greater than or equal to -8 when plugged into this inequality will result in a true statement. Okay, so you could plug in -8 since x can be greater than or equal to it, and if you put -8 in here, 5 plus -8 is -3, which would make this a true statement because -3 is greater than or equal to -3. Okay, specifically, they are equal. And you could test other numbers as well. If you picked a number bigger than -8, such as 0, and plugged 0 in here, 0 plus 5 is 5, and 5 is greater than or equal to -3. Okay, but if you picked a number smaller than -8, then the resulting statement would not be true. Okay, but this is the solution set. We have solved for it, but we don't want to forget to plot it or graph the solution set on a number line. So I will draw a number line here. I always let the middle be 0. And then in this case, the number we are comparing x to is -8. So this is -1, -2, -3, -4, -5, -6, -7, -8. So label that. And then x can be greater than or equal to that value. So we can draw a closed circle at -8 because we will include that number in the solution set. But then after that, we want to include values of x greater than -8. So that would be all numbers to the right of that number on the number line. Okay, so you could add other tick markers here if you wanted to, but it's not really necessary. You can just draw an arrow from that point at -8 and point it to the right, and that indicates that the solution includes all values of x greater than or equal to -8. Okay, let's take a look at one more example for this video. For our last example, we want to solve the inequality and graph the solution set on a number line. and we've been given the inequality 5x minus 6 is less than or equal to 4x minus 4. Okay, so this inequality is a little more complicated than our previous two inequalities because it has a variable term on both sides of the inequality. But remember, the addition property for inequalities applies to both constant terms and variable terms. So really, you can treat this just as if it was an equation. It doesn't matter that you have an inequality symbol here. You can still add or subtract variable terms or constant terms from both sides of that inequality, just like you would for an equation. All right, and so looking at these two variable terms, they do have the same variable part of x, so they are like terms, which means that they will combine nicely when we try to get rid of one of them from one side of the inequality. Okay, because our goal here is to isolate the variable or get it by itself, and in order to do that, we have to have just one variable term or just one term involving x, not two of them. All right, so the first thing I want to do here is remove one of these two variable terms so that I only have one. And for this inequality, I think it makes sense to remove 4x from this side of the inequality. What I mean by that is we want to add the opposite of that term to both sides, or in other words, subtract 4x from both sides of the inequality. Okay, because 4x minus 4x would be 0, so those terms cancel out, and then 5x and negative 4x are like terms, so you can combine their coefficients, and 5 plus negative 4, or 5 minus 4, is 1, so you just have 1x, which we would represent with just x. Okay, and so then rewriting everything else, we have x minus 6 is less than or equal to negative 4. Okay, that other variable term is now gone. Now, a quick side note here. Yes, you technically could also solve this inequality by subtracting 5x from both sides of the inequality. But if you did that, you would have 4x minus 5x, which would give you negative x. And so x would have a coefficient other than 1, which we haven't talked about how to deal with yet. So for right now, we're not going to worry about that. We'll talk about that in the next lesson. In this video, we're just focusing on the addition property of inequalities. And so in more complicated inequalities like this, I'm always going to be looking for which variable term can I subtract from both sides, such that I am just left with positive x on one side of the inequality. Okay, that's going to be my approach for right now, but in the future you don't have to do that once we learn other properties of inequalities. Okay, but putting that aside, we're almost done here. We still need to isolate x or get it by itself. We haven't quite done that yet. This is not in the form of a solution set. What we need to do is get rid of this negative 6, and so what we can do is add the opposite of that. In this case, that would be positive 6. So let's do that here. Let's add 6 to both sides of the inequality. Negative 6 plus 6 is 0, so those cancel out, leaving us with x is less than or equal to negative 4 plus 6, which would be positive 2. And so x less than or equal to 2 is the solution set to this inequality. Okay, so you could pick any number less than or equal to 2 and plug that in for x in this inequality, and you will get a true statement. All right, but then to finalize our answer, we do want to graph the solution set on a number line. So I will draw a number line here. In the middle, I will have 0, and then we're comparing x to 2 in this case. So 1, 2 would be right here, and x can be less than or equal to 2, so we can include that value of 2. So I will draw a closed circle, and then we're including values less than 2, so we want to point the arrow in this direction. Okay, all values to the left of 2 on the number line would be values less than 2. Okay, and so with that, we have finished this example. This is the solution set to this inequality and its graph on a number line. And this was also the last example for this lesson video. But if you do want to get some more practice solving inequalities using the addition property, feel free to check out my examples video for this topic that I'll have linked here on the screen. If you have any questions, please let me know in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.